In this ClimateGenn episode, I'm speaking to Dr Levke Caesar about the Atlantic Meridional Overturning Circulation, or Amoc, about what would happen if this vital piece of the climate system either slowed dramatically or even shut down altogether. Although climate models indicate this as low risk, to date the models have been poor anticipators of the speed of localised climate changes. Levke gives an insightful and sincere perspective on the importance of the Amoc as a critical piece of the climate system jigsaw. In the next episode, we stay in the oceans and speak with Dr Shaun Fitzgerald, Director of the Centre for Climate Repair in Cambridge, about the collaborative effort they are involved with to develop kelp seaweed for both carbon sequestration and the benefit of marine ecosystems and more. Subscribers via Patreon can also access another episode with Professor Bill Maguire discussing his new book Hothouse Earth, and very shortly a new interview from my visit to the Monaco Scientific Centre to interview Dr Natalie Hilmy about the centre's work in ocean research and conservation with corals and whales among other marine ecosystems on the agenda. Please do also check out the Sustainability and Alentejo wine series that I've been posting. The latest episode features an interview with Professor Kimberly Nicholas at the University of Lund in Sweden about regenerative practices that underscore the critical importance of learning to work with nature rather than against nature. Thanks for listening to ClimateGenn. Please do like, follow, share or subscribe if you can. Levke, thank you very much for speaking to me today. It's great to be able to talk to you about this subject. Can we start by you giving us a sort of broad brush overview of what we mean when we refer to the Atlantic Meridional Overturning Circulation, or Amoc as it's more commonly referred to?
Yes, sure. So basically, when we talk about the Amoc, we actually talk about a system of ocean currents that span the whole length of the Atlantic. So really starting basically in the Southern Ocean, entering the South Atlantic. And then what we mean with Amoc are the warm and relatively salty water masses that are traveling northward in the Atlantic, basically at or just below the surface. And so we have this huge flow of water masses and they're crossing the equator, continue to travel northward. And then as they're getting more and more north or into the colder regions, basically, the overlying atmosphere is cooling these water masses down. So they're getting colder, and colder water is denser than warm water. And then at certain places in the subpolar North Atlantic, often actually kind of close to Greenland, these water masses start to sink, and they're sinking to deeper ocean layers and then form a southward return flow of water. Basically, now we have colder water that is flowing southward. And because of this inflow of warm water in the subpolar North Atlantic, the outflow of cold water, we associate the Amoc, or the Atlantic Overturning Circulation, with a large heat transport within the Atlantic.
One of the things we do hear a lot about is the decline in strength. What are the sort of factors that you're analysing when you're trying to figure out whether it's increasing or decreasing in strength?
That's actually quite complicated to do. So, I mean, ideally, if we want to know whether something is changing, you would say, okay, you just measure it directly, right? If you do direct measurements and then you just observe it over time, then you would know whether something's changing or not. And we're actually doing that with the Amoc, but the direct measurements only started in around 2004. Basically only then, because it's so complicated to measure. I mean, it's an ocean current or a system of ocean currents. So it's not really localized in space, but it's kind of can be wiggling around a little bit. The exact location can shift a little bit. And actually, ideally, you would have to measure it at various places in the Atlantic to really get the full picture. And then in 2004, basically, they put an array of different instruments into the ocean, and then they keep them there for a year or a year and a half. And then they have to take them out, get new measurements in. And by doing that, we got a fairly clear picture of what the Amoc has been doing since 2004. And since then, we have seen a decline in strength. So you could really just measure that. So how much water is basically traveling northward and how much water is then traveling back south. But 2004, that's 18 years ago. And when we look at a time series over 18 years, we can't really say whether we see any sort of climate change. I mean, with climate or the climate system, you can have different definition of what exactly do we mean with climate, but a common definition is actually to say it's our weather averaged over 30 years. So basically, we don't talk about climate change when we have a hotter summer this year than last year, because that's basically just the chaotic component of weather. This time series since 2004, it's not long enough to really tell us what's the cause or whether this is a long-term change or, the idea is it could be some kind of eternal variability of the Amoc. So we have also components of the climate system that don't just have an annual cycle, but a cycle over, multiple years or sometimes even decades. We then try to go back in time and try to understand or know something about the Amoc before 2004. And one way to do that, or one thing to look at, was basically just the temperatures in the North Atlantic, or specifically kind of the region south of Greenland, which we call the subpolar North Atlantic in climate terms, basically, because we know that the Amoc is transporting so much heat into this region. So you can kind of say, okay, if we just basically observe or track the heat content evolution or the temperature evolution in this region, this gives us kind of a status report on the strength of the Amoc. This is a pretty good idea, but of course you have to then take care or note that, of course, these temperatures in the subpolar North Atlantic can also be influenced by other factors, just basically the overlying atmosphere. For example, if you have stronger winds over a certain region, then the stronger winds will take the moisture, the heat faster away, and you can also cool down the ocean surface. So you kind of have to take that into account too. And we try to do that. And this then gives us an estimate that the strength of the overturning circulation slowed down by about 15% since the mid-20th century, just by seeing this localized cooling in this region south of Greenland, which is in stark contrast to the rest of the globe, where you can really see the effects of global warming.
And is there any impact of things like meltwater from Greenland or any other currents that you can, I know you've been looking at it for too short to really identify this, but do you have theories on how these things might interact that seem to be playing out in the data?
Yes. So, I mean, first of all, we can look at two different things here, right? On the one hand side, we can look at what is influencing or impacting the Amoc, and then we could look at what is the Amoc impacting, or what impacts does the slowdown of the Amoc have. When we look at what is impacting the Amoc, basically, so for what we did actually for the past is that we characterized or found the slowdown, but we didn't do any kind of an attribution study. So we are not 100% sure what has caused this. We have, of course, certain ideas because we understand certain mechanisms, which is, for example, that we can see in climate models that the increase in greenhouse gases is actually causing a slowdown of the overturning circulation, while, for example, an increase in aerosols concentration in the atmosphere can strengthen the overturning circulation in climate models. You can understand this, or ways to understand this, because this is, of course, like the one end of a chain and the other end of the chain. So you're kind of wondering, okay, what's happening in between there? Why do we have this link of more greenhouse gases means slower overturning circulation? And looking at it in more detail, trying to understand the physical processes, what we know is, of course, under increased greenhouse gases, we see global warming, and we see an increased melting of the Greenland ice sheet. When we just look basically now at the subpolar North Atlantic, where the Amoc stuff is mainly happening, we see an increased melting of the Arctic sea ice. We actually see increased river runoff, so basically river water being brought into the subpolar North Atlantic, and even increased precipitation. Increased precipitation is per se not a global signal. So what we see under global warming is just an intensification of the hydrological cycle, kind of in the sense you could say that wet regions are getting wetter and dry regions are getting drier. And the subpolar North Atlantic is a region where we normally have precipitation, and this seems to be increasing under global warming. Now, I'm listing all these processes because they have one thing in common. Mainly, they add fresh water, so water that is not salty. So precipitation, rain is fresh water. what we're drinking is fresh water, into the ocean or into the subpolar North Atlantic there. And by doing that, they're basically diluting the surface waters. So the salty surface water that are being brought by the Amoc to the subpolar North Atlantic, they're getting less salty, and less salty means they're getting less dense. And less dense water means it's lighter, so it's easier for the water to actually stay at the surface. So the sinking process, which is one of the main drivers of the Amoc, is being slowed down. And with that, the whole cycle of the overturning circulation is or can be slowed down. And we think that this is actually the processes, one of them, a combination that would slow down the overturning circulation. And we are not quite sure which is right now the dominating one. Like, is this the melting of the Greenland ice sheet, which has been increasing over the past years, but which in total numbers is still fairly small compared to the size of the ocean. And we don't really know what it is, because this sinking of water masses, the deep water formation, this driver of the Amoc, that's actually a pretty localized process. So it's not that you have this huge area where all the water masses are sinking and, forming like a deep hole, but it's rather something that's occurring mainly in the wintertime when it's especially cold, the surface water is especially dense, and then it's more localized that you have like downbursts of water masses. So it really matters, where is this freshwater input in the North Atlantic? Where would it really slow down the process, and where would it not really matter? We could say, freshwater in that area, that's all right. And so it's really hard to see that or to model that, because climate models are good on bigger scales. They're not that great on the really small scales.
And when we talk about the Amoc from a British perspective or an Irish perspective, we tend to be more worried about it because we seem to be in the sort of line of as it's traveling up to the north. What would be the biggest concerns of it slowing down in terms of impacts on the United Kingdom or Ireland?
Well, that's a good question. I personally would be worried about the impacts on weather dynamics it basically can have. Those aren't fully understood yet, but we have indicators from different climate models where you basically force the Amoc to shut down, that at least such a strong change in the Amoc, and perhaps likely also smaller changes, can lead to an increase of the storm activity over the North Atlantic. And as you said, we're kind of like in this pattern then, or in this pathway of wind storms coming from the North Atlantic. And so we could have an increased number and intensity of winter storms hitting Ireland, hitting the UK, particularly in the winter times. And of course, storms can be devastating. Always really depends on where they hit. Then I'd say it's also, and this is maybe more the importance of what do we have to expect in the terms of we are in a world with a changing climate, right? And I mean, that's alone, just looking at the consequences of the impacts of what is global warming doing, where exactly do we expect how much of global warming? We have rising sea levels because the ocean is warming up, and warmer water, less dense, it's expanding. So we kind of, I guess, at the moment start to try to adapt to this warming world. But if the Amoc would shut down within the next decades, then this is actually going to lead to a harsh localized cooling over the North Atlantic or within the North Atlantic region. So for Ireland, the UK, that would actually make a great difference. I guess we don't even have to talk about what's better or worse, because both has lots of consequences, but it would definitely be a very different climate. And I mean, adaptation, you don't adapt to changing climate within half a year or a year, but you really have to plan, right, in terms of building dams and changing the way you're building houses and so on. So the Amoc, as I said, is bringing more heat into the North Atlantic, and more heat actually normally means that the atmosphere can carry more moisture with it. So I would say a shutdown of the Amoc is likely rather to cool the place down and to make it a little bit drier, at least in the winter time. I'm not completely sure about the summertime. Right now, I'm basically talking about thermal changes. As I said, kind of, do we expect more or less heat and so on? That's difficult enough to kind of predict for the future, but it's even more difficult to predict changes in circulation patterns. And that's actually something that could also lead to a lot of changes. I don't know whether you kind of heard about the jet stream and the wave patterns of the jet stream have been talked about a lot recently, because those wave patterns often depend on where weather systems are located over the northern hemisphere, over the mid-latitudes in the northern hemisphere, and how fast they're moving. And it is possible that Amoc changes can kind of also affect this dynamic patterns of the atmosphere. And those can then, I'd say, rather fastly and actually in kind of a large amplitude suddenly change the conditions in a certain place, because they can determine on whether or not you get the air from the south or whether the air is coming from the north. So do you get warm and moist air or really cold and dry air? And we don't know enough about that yet, since it's kind of difficult to model. And that's basically where we get our information about the consequences of an Amoc shutdown, is mainly from models. I guess regions that will definitely feel the impact of an Amoc shutdown in terms of precipitation are actually the equatorial regions. So Africa and Asia, in terms of the monsoon systems there, because what we have roughly above the equator is what we call the intertropical convergence zone, which is basically when you look at the planet as an astronaut, you would kind of see that there's like this bands of clouds above the equator. So you kind of see this white band. And that's basically determining where does it rain in the equatorial region, where does it rain and where is it dry. And we know that this intertropical convergence zone, the exact position of it, at least in the Atlantic area, is also determined by the strength of the Amoc. So an Amoc shutdown is going to shift this bands of cloud, and it's not going to take away the rain. It's just going to change where it rains. And that, of course, could be devastating for the food production there, because obviously agriculture and so on is used to certain cycles, and you're kind of normally getting used to getting the rain there. So you grow your crops there. And when the rain patterns are shifting, again, we would have to adapt to that.
Is all of this becoming sort of more complex by having so many changes within the Earth system and from a generally changing climate? So even if the Amoc was to slow or shut down, then there are other factors also creating other impacts.
Exactly. And that's really the problem in determining attribution and saying, okay, what is causing what? And then also what effects do we see when something is happening? Because even if we know exactly what the consequences of just an Amoc shutdown would be, then we would have to say, well, we're not just looking at an Amoc shutdown, we're looking at an Amoc shutdown under global warming. And that, of course, will lead to a superposition. And then, as I said, it's kind of when we look at climate projections, we're pretty good at the large scale. So kind of saying, okay, the rise of the global mean temperature, there's still uncertainties often related to our behavior, because it really depends on the human behavior and our emission of greenhouse gases. But that's fairly certain to predict. But the more localized you look at, that's really complicated.
I know you won't have a sort of a certain answer to this, but how much, I'm sort of referring to scientists I've spoken to over recent months who work in places like Greenland. And one of the phrases that comes up a lot is faster than forecast. And is there a worry now? Do you think that these scenarios are riskier or happening faster than we thought they might? And therefore, the risk of a shutdown is still low probability, but it's something that we really should understand in much more detail. I'm sort of trying to, without sounding doomy or anything, I'm just trying to gauge how much you're concerned about the risk of it.
Well, that's a good question. It's actually a topic that is worrying me. Because, as you said, there are some processes in climate, like melting of the Greenland ice sheet, melting of the Arctic sea ice, especially in the summertime, that have been happening faster than we predicted with our climate models, and sometimes at rates that are way faster than we predicted. And I would say that, first of all, when we look at the responses in climate models and we kind of give a range and the best estimate, then there might be a 50% chance that the consequences are less than we predict, but there's a 50% chance that they're worse or faster, stronger, whatever than we predict. And I guess when we talk about this Amoc shutdown, sometimes we have this term of a low probability, high risk event. And I'd say I definitely agree with the high risk, in not necessarily because we completely understand all the devastating consequences, but because there's so much we don't know about what's exactly happening when the Amoc is shutting down. We just know that it's a huge system. It's affecting the whole North Atlantic, the marine ecosystem. So we know it basically has its hands everywhere. So seeing that a shutdown just would have to affect a lot of things. Maybe not all consequences would have to be negative, but there would be an awful lot of consequences. And then we're saying it's a low risk event. And we're saying that basically because most of our climate models say it's not going to shut down within the course of the 21st century. And we're looking at our climate models, it's very unlikely for the Amoc to shut down unless we have at least 4 or 5 degrees of global warming, and probably or might even only happen with 6-7 degrees of global warming. But then again, for example, we see, as I said, we kind of look, for example, at the temperature evolution in the subpolar North Atlantic that kind of indicates that the Amoc has been slowing down over the course of the last century already by about 15%. And there actually are other data coming from ocean sediments, and mainly from ocean sediments. A little bit complicated to explain in such an interview, but there are other indicators kind of saying, yeah, probably it already started to slow down. And hardly any of our climate models predicted that. Mm-hmm. So they might not be that good in the sense all our climate models predict that the Amoc will continue to slow down over the next 100 years and probably beyond that. So we're fairly certain that's going to happen. But seeing that, that they didn't do the greatest job at doing the historical slowdown. And also there are still problems in modeling the overturning circulation because it's such a complex system. For example, just when we look at the mean strength of the overturning circulation, so when we have a stable state in the different climate models, then we have a variety of mean state strength. And of course, in the real world, we have one mean strength. So I'd say, the uncertainties are really, really big. And there was one study last year that kind of looked at kind of the statistical analysis of time series. You can kind of look at how the variability of a time series or of a system is changing. And as I said, the Amoc has some natural variability. And well, when the variability is changing in the sense it's basically the wiggles are becoming more pronounced or it's staying longer in a wiggle before it's returning to its mean state, this could indicate that a system is destabilizing. And there are some points or evidence saying that, the Amoc might be destabilizing. So, I'd say it's a difficult topic, right? Because, we're not winning anything by worrying all day about it. Like just being worried all day, that's not going to win us anything. But we definitely have to understand it better. And as I said, also, it might be hard to prevent it happening. So if we are unlucky, then basically we're already on the move of the Amoc just getting slower and slower. But at least we would have, if we knew about it, at least we could then kind of try to prepare for those changes, even if we can't prevent them. So
this, just to be clear, this would have impacts right across Europe, Africa, northern, all over the place. This would have serious impacts.
Yeah, even the southern hemisphere, because we have the sea transport by the Amoc from the southern hemisphere to the northern hemisphere. So the southern hemisphere would likely experience more global warming, and we would see some cooling here.
Okay. And all of these things would, accelerate sea level rise if you're increasing the warming in the southern hemisphere.
Exactly.
Okay. Well, you've given us a fantastic overview. Can you tell us a little bit about, in your Amoc related work, what you're looking at right now and what the most interesting thing is sort of coming out of it at the moment?
Yes, I'd say on the one hand side, we are really trying to understand why we have those evidence from the different, we call it proxy data, so indirect measurements of the Amoc that point at this historical slowdown, while we did not see that in most of our climate models. So most state-of-the-art climate models said, okay, the slowdown is actually only going to start basically at the moment, maybe plus minus 10 more years. So we're trying to understand that. see. One idea is, for example, that the climate models overestimated the response of the overturning circulation to aerosols. As I said in the beginning, that aerosol concentration, increasing that can actually strengthen the Amoc a little bit. And our climate model might have overestimated that. So they were able to simulate the slowdown, but also predicted in strengthening. So it kind of remained stable. That's one of the big questions. The other is that when we talk about the Amoc, we sometimes call it the conveyor belt. And I guess this kind of gives the impression that we really have like a loop system that is closed. And that's not really the case. So it's way more complex than that. And it seems to be we're trying to understand whether it's maybe possible that measuring the Amoc at a certain latitude, for example, looking just above the equator, whether this strengths really translate into looking at the Amoc, close to Greenland, whether we really have this close connection or whether this actually on timescales of a few years might be kind of, detached from one another. So really to say, okay, how connected is this Amoc really? And on what timescales is it really connected? Then, of course, this question about the shutdown of the Amoc, pinpointing, okay, how much global warming can we have before the Amoc shuts down? Because that hardly changed over the last 20 years. I would say we might understand the uncertainties a little bit better now that are related to them, but the actual size or range of the uncertainties hardly changed. And that's a little bit frustrating, of course. Yeah, I'd say that's probably the big questions. And then kind of more recently, trying to understand a little bit better in how far does the Amoc affect the weather and storm systems. So both actually on both sides of the Atlantic. So in terms of hurricanes for the US, and then winter storms, but also, as I said, this wiggles of the jet streams, and with that actually extreme weather events like heat waves, droughts, and so on. So yeah, lots of questions. I guess I could actually go on and go on, but I'd say those are the big ones.
Okay. But there is a very strong link to the temperature of warming that we're getting. If we continue to heat, if we continue to emit, we're going to keep seeing the risk increase as well. So these are all completely linked.
Yes. At least all the evidence we have nothing that would point to the contrary. So we can likely say if we have more global warming, then it's more likely that the Amoc is going to slow down more and more.
Okay. Well, look, thank you very much for taking the time to speak to me. It's been very, very interesting. And hopefully we'll speak to you again when you've got an exact day for when it's going to shut down.
Sure. Sounds good.
Thanks again for listening. If you are interested to help support this series and help expand the discussion around climate topics, then please do consider backing my channel via Patreon. It will help me produce more content, and you will also gain access to more expert interviews. It would be great to engage more with audiences too and understand your views on these topics.